All right, take 6, I believe. Welcome back to the new and improved Discrete Math. It's now 10:56 p.m. on Friday, March 20th. I'm trying to get a head start making these videos so that I have something to upload on Monday while I figure out the best way to proceed. As I explained in the email I sent, I don't yet have all the details for how everything's going to work going forward. But I will be obviously recording my lectures from here on out. I think I will figure out where I'm posting them by the time you see this, of course. So I won't go into that. So for this first video, let me just briefly recap where we were at with the new material from chapter 8. And then go a little bit further into the next section of chapter 8. Maybe I should say my plan for the remainder of the semester as far as material goes. I want to cover at least parts of chapter 8 and probably parts of chapter 10. But really, this is... I'll edit out this pause. We'll do what we can. All right. All right, so if you'll recall, we were talking about recurrences, recursion, solving recurrences. And just to remind you of one of the examples, we had the Towers of Hanoi problem, where we had the 3 pegs, and on one of the pegs we had a tower with disks of decreasing size, and not to go over all the rules involved, but they were in disks. We could move one disk at a time, and the rule was that a disk can only be put on top of disks that are larger than itself. So our goal is to move the entire tower to a different peg, and H sub n was the minimum number of moves required to transfer the tower. I don't know why I'm writing all this again, but okay. Hopefully my handwriting will get better as we go. All right. So we solved this, just to briefly recap the solution. Well, sorry, first off, the recurrence first. So H0, our base case. H0 is the number of moves required to transfer a tower of size 0 from one peg to another. Well, if there are no disks in our tower, it takes 0 moves to transfer that tower. Right? And then, in general, the recurrence relation for Hn. If we're going to move this tower, I have to move the biggest disk, but before I can do that, I have to move the entire stack of n-1 disks from on top of the biggest disk to a different peg. That takes Hn-1 moves. So now we've moved the smaller tower over. Then we can move the big disk to the third peg. That's one more move. Then we have to move the smaller tower back on top of the big disk. So that takes another Hn-1, so that gives us 2 Hn-1. Okay, so for n bigger than 1, n bigger than or equal to 1, we have this relation. Hn is 2 Hn-1 plus 1. All right, so I'll rewrite that. And so the recurrence that we had was this. So we want to solving that recurrence means finding a formula for Hn. So some formula involving n that satisfies this recurrence. And so we did that with this iterative method where we just keep applying this recurrence until we get down to H0, and then we have a formula that we had to simplify. And that formula turned out to be, so let me write the solution was the formula Hn equals should be 2 to the n minus 1. Okay, so not to redo the work of deriving that, but let's do something that I think we did not do in class already. Let's check that this actually is a solution. So to check that, what we want to do is that we want to check that it satisfies both of these equations. So this is the easy one. If I plug in 0 for n, I get 2 to the 0 minus 1. That's 1 minus 1, which is 0. So that satisfies the initial condition there. For the other one, let's check that this formula satisfies the recurrence. And let's do it by looking at the right-hand side and simplifying it to get the left-hand side. So 2Hn minus 1 plus 1. If this is the formula we're using, then we got 2Hn minus 1 is this with n minus 1 plugged in. So 2 to the n minus 1 minus 1. Forgot my 2. We already have a 2 here. Hn minus 1 is this with n minus 1 plugged in. So there's Hn minus 1. And I've got plus 1 after that. Alright, so now if we simplify this, distribute that 2, we've got 2 to the n minus 2, and then plus 1. That gives me 2 to the n minus 1. And that's exactly my formula for Hn. So, using this formula for Hn, we have a we've satisfied the recurrence. Right? So, once we have a formula, checking it as a solution is just verifying that it satisfies each of the conditions. The recurrence is the big one, and then the initial conditions, whatever they are the easy ones. So the difficult part is coming up with the formula in the first place. And so if you'll recall, for this example, it was not that difficult. We could run through the recurrence again and again until we got it down to a formula that we could simplify. But that's not it's not a effective way of approaching these problems in general, because as we've seen with some of the other examples, the recurrences can get very complicated very quickly. All right, so as we go, I'll remind you of some of the other examples we looked at, but let's do some definitions. So here's where I think we actually get into section 8.2. Linear recurrence relations is what I have in my notes. Abbreviate that to linear recurrences. Okay. So we are going to be talking about a very special case first, a very special type of recurrence. So lots of adjectives here. A linear, homogeneous, recurrence relation of degree k with constant coefficients has the form, let's see if I can move this way, right, has the form, all right, or can be written in the form a sub n equals, and now it's going to be a linear combination of earlier terms. So I don't know, a number like this, c sub 1 a n minus 1 plus c sub 2 a n minus 2, and so on until the last term would be c sub k, that's the degree here, a sub n minus k, where each ci is a constant. Remember, our variable here is n, so when I say constant, it means a number, not, it has no n's in it involved. So each ci is a constant. So let's talk about this and the different pieces of our definition. So the constant coefficients, that's the c's. The ci's are constants. So the things being multiplied each of these previous terms. So we have these a sub n minus somethings. These are earlier terms in the sequence an. Okay, so a solution to this would be some formula for an involve some function of n for your formula for an. So once you have that, you know what an is, you know what an minus 1 is, an minus 2, and so on. It's all based off of the same formula. But the coefficients on those earlier terms, those are constants. So that's the constant coefficient part. The degree k means, I guess I should make one more note here. ck specifically is not 0. So some of these c's could be 0, so maybe not all of these a's appear. But this one definitely appears with a non-zero coefficient. So that's the degree. The degree tells you how far back in the sequence your recurrence looks. So the example we just did with the towers of Hanoi, that was degree 1 because the recurrence only involved the immediately preceding term. Okay, so that's the degree. Homogeneous. Homogeneous refers to the fact that in this sum, every single term involves an a. So every single term in this sum involves an earlier term of the sequence. So if I put like a plus 2 at the end of that with no a involved, just like plus 2, that would be non-homogeneous. So every term has to have an a in it. And finally, linear means two things. These a's don't interact with each other. They don't get multiplied or divided by each other. They can't be multiplied times themselves, so we can't have exponents on the a's. The linear just means we have a linear combination of these a's, and the constants are the coefficients are constant for the constant coefficient part. Okay, so these definitions are complicated or confusing, so let's just go through some concrete examples and classify them with these different adjectives. Let me erase this. So one we already looked at was the Fibonacci sequence. I think I used R's before for rabbits, but let's just use F's. The Fibonacci sequence's recurrence was Fn equals Fn minus, I guess I should be consistent, Fn minus 1 plus Fn minus 2. So in other words, to figure out the next term, we add up the two immediately preceding terms. Okay, so this is linear. because these two f's are separate, they're not multiplied, they don't have any exponents on them, there's no division, so it's linear. It's homogeneous because this side of the equation only involves f's. It doesn't have an extra +2 or plus n. It doesn't have a plus anything else that doesn't involve f. So it's homogeneous. Its degree is 2 because we used 2 terms earlier. So we go back 2 steps to see what we have. I guess there's no check mark there. It's just degree 2. It's got constant coefficients because each of these f's has coefficient 1. Okay, so that one is an example of one of these things. Let's do one that's not all of them. Okay, so this is not what we've seen before, but just an example. If we had the recurrence an equals an minus 1, I think we did, maybe this one is an example we looked at already. So an minus 1 plus n. We either did this exactly or something very similar. I can't remember. So I didn't explicitly define all the things as clearly as I maybe should have. But this is linear because we don't have any multiplications or exponents on a's. All the sequence terms only appear as themselves, no multiplication between them or no exponents on them. However, this one is not homogeneous. So this is non-homogeneous. Because of the n. So that term there has no a on it. So it's got I can't remember the term in the word in the book. Non-homogeneity, inhomogeneity, something like that. Some extra function that's added to the end of our recurrence relation. So it's a non-homogeneous linear recurrence. Its degree is 1 because the only previous term that gets used is n minus 1, the one that comes right before the one that we're looking for. We look 1 step back, and that's our degree. All right, I guess it's also constant coefficients. That's a little bit trickier what we mean by that. The constant coefficients we're referring to are the things being multiplied by the previous terms. So any a in our recurrence only has a constant coefficient. So let's maybe do one that has non-constant coefficients. All right. All right, so another one, we'll switch that up with b's for fun. So bn equals n bn minus 1 plus 2 bn minus 3. So let's do the easy thing first. This is degree 3 because our recurrence involves bn minus 3. We have to go back 3 steps in our sequence in this recurrence. This is still linear because there's no interaction between the b's. This is still homogeneous because every term has a b in it. But we have non-constant coefficients. Because at least one of our b's, the coefficient is not constant, it's a function of n. It depends on n. So n bn minus 1, that part there has a non-constant coefficient. but it's still a linear recurrence. Okay. Okay, so maybe do one more example. It just occurred to me though, if you ever have questions about things that I'm talking about in these recorded lectures, you have a couple options. If I successfully post these on YouTube, you can, if you are able to, you might be able to post comments on there, which I can see, and then either, if it's simple, I can respond to it as a comment, or you can also email me questions about each lecture. Just make sure you tell me which one you're talking about, and refer with as much specificity as you can. I'll try to do better about numbering my examples as we go farther on. But in any case, if it's a question I can't answer very well through email or through text, I can make separate videos responding to student questions. If I accumulate some questions, I can make a separate video to cover those. But let's press on. So one more of these examples. Let's do this. So if I have a recurrence an equals an minus 1 times an minus 2 plus an minus 4 squared. This would be an example of a nonlinear recurrence. It's nonlinear for two reasons. One is that an minus 1 is multiplied by an minus 2. So we have two different terms of the sequence being multiplied. So that's bad enough to be nonlinear. But we also have a power of a previous term. So an minus 4 is being squared, so that makes it nonlinear. So it's nonlinear. Its degree is 4 because we our farthest back term is n minus 4. When it's nonlinear, we don't really worry about, well, for our purposes, we're not going to be solving nonlinear recurrences, but with nonlinear, we're not classifying according to the same standards that we use for linear recurrences. For linear recurrences, we care about constant coefficients versus non-constant, and we care about homogeneous versus non-homogeneous because it determines the methods that we'll use to solve them. For nonlinear, that's all out the window. We don't really worry about constant coefficients or homogeneity because it's a completely different ball game with nonlinear. So I'm not going to worry about, does this have constant coefficients? I mean, I guess it does, since all the numbers are constant, and I guess it would be categorized as homogeneous since everything does have a's involved. But we're not going to worry about that. All right. What we are going to worry about is how to solve linear recurrences with constant coefficients, both homogeneous and non-homogeneous. But for now, we're only going to worry about homogeneous, and we'll come back later to do non-homogeneous. Okay, so figure out be judicious about my board space here. So this is probably a waste of space. So what I want to talk about here is just a preliminary discussion on how to solve a linear homogeneous recurrence with constant coefficients. All right, so let's write one of the generic recurrences. An equals C1 an minus 1 plus C2 an minus 2 all the way up to CK an minus k. so this is going to be our recurrence. Let me label it star. And I'll keep that around as we go. All right. So with a little bit of hand waving here, let's suppose I have a basic solution to this. I have some formula for AN that satisfies this recurrence. And I'm going to suppose that AN is of the form an exponential function r to the n for some r. So some number r. Okay, so we're kind of working backwards. How do we know that it would have this form? Well, we don't really. We'll address some of those issues later. But let's suppose that we have a solution to this recurrence and it has this form. Well, let's plug this function in place of the a's now. Then star becomes a sub n is r to the n. R to the n equals c1 a n minus 1 will become r to the n minus 1. Because remember, whatever the subscript is, that's what I'm plugging in place of n. Plus c2 r to the n minus 2. All the way up to ck r to the n minus k. Okay, so it doesn't... I don't know how legible it is. My screen has it all reversed. I'll try to write bigger. All right, so we've got this equation now. It looks very similar to the original one. Basically, it looks like our subscripts became superscripts, but now superscripts are exponents. So let's try to simplify this a little bit. So if we look at this, every term has some power of r. And so the fewest powers of r occur here, r to the n minus k. So if I divide the entire equation by r to the n minus k, my equation is going to become, well, if I divide it from r to the n, and then I cancel out n minus k, I'll be left with k, r to the k. So the left-hand side becomes r to the k. And then each one of these, I'm going to subtract n minus k from the exponent. So I'll get c1 times r, n minus 1 minus n minus k will be k minus 1, plus c2 r to the k minus 2, and so on, until at last I get just ck. All right, so I think that's... All right. So now this equation still doesn't look that impressive, but the point is, or one point is, even at this point, this equation is now a polynomial. If you think of r as a variable, this is a polynomial equation. Let's get everything to the same side. We have r to the k minus c1 r to the k minus 1 minus c2 r to the k minus 2 minus ck. This all equals 0. Okay, so this equation here is an important one. Let me keep it around for just a second. Let me erase some of the stuff so I can write some other things. This here, I'll put double star or something. This double star equation is called the characteristic equation for the recurrence, which was star. Okay. So, I'm thinking of r as a variable here, but remember the point was, if r to the n was going to be a solution for an, so r to the n is a solution for this recurrence, r has to satisfy this equation here. So the solutions, if you want, you can replace r's with x's maybe, but let me just keep it r. The solutions, which for emphasis are r values, are called the characteristic roots. Okay. So let's talk about a simple case first, a simpler case first, and then we'll do some specific examples of what this all means. Okay, so let me write the theorem for a simple case first. This is the degree 2 case. Alright, so the recurrence is, a degree 2 recurrence would look like an equals c1, an minus 1, plus c2, an minus 2. So that's what we're trying to solve, or that's what we want to solve. Then if we do the same thing we just did, the characteristic equation, let me abbreviate, would be, well, what you're doing is replacing an with r to the n. So you're basically changing the subscripts to superscripts. And then you're dividing out n minus 2. So my characteristic equation would end up being r squared minus c1 r to the first minus c2 equals 0. Right. So we get some polynomial. Now think of r as a variable. And there's two cases. I'm going to have to write them one at a time on this board. I don't have enough space for both at the same time. Keep with my notation from the previous board. We'll call the recurrence star, the characteristic equation double star. So we're looking at the roots of the characteristic equation. If double star has two distinct roots, R1 and R2, then let's say any solution to the recurrence star, so the recurrence has solutions of the form, or has the form an equals, and what we're going to have is a linear combination of exponential functions with these roots as the bases. So it'll look like this: alpha 1 r1 to the n plus alpha 2 r2 to the n, where alpha 1 and alpha 2 are any constants. So I think my wording got a little bit garbled here, but let me repeat it clearly here. So once we find these two roots to the characteristic equation, then if I write a solution like this, an equals alpha 1 r1 to the n plus alpha 2 r2 to the n, where the alphas are any numbers, that will give me a solution to the recurrence. And what's more, any solution to this recurrence will have the form matching this for some alpha 1 and alpha 2. So the correct numbers to use for the alphas will depend on what the initial conditions are. Like if I know what A0 is supposed to be and what A1 is supposed to be, I can figure out what alpha 1 and alpha 2 are. Okay, so we'll do examples shortly. Well, we'll do examples eventually for that. Okay, but there are two subtle parts to this statement here. One is anything of this form is a solution to the recurrence, and every solution to the recurrence can be written in this form. Okay, so let's maybe do an example of a specific recurrence and that works like this. And depending on how long that takes, I'll maybe cut the video and do the next case in the next video. Okay, so let's erase this. Which means I have to write it up again for the next time we do case 2. But okay. Don't think I want to do Fibonacci sequence right off the bat, so let's do a simpler example. So an equals an minus 1 plus 6 an minus 2. Okay, so I want to find the general solution So if you've taken differential equations before now, this is very similar to differential equations. So if I just have a recurrence, that's like I just have a differential equation. There's a whole family of sequences that satisfies that recurrence. There's a infinite family of solutions to this. So the general solution is going to have some unknown constants, the alphas from what I wrote before. If we have more information, like the initial conditions, like A0 equals 1 and A1 equals 5 or whatever, then we can narrow down our general solution to a specific, or rather a particular solution where we fill in the values of those constant alphas. Okay, but for now, let's just worry about the general solution. So first thing is we need the characteristic equation. And I'll go through it carefully this time. So rather than memorize what it looks like, remember what you are doing is basically replacing the A's with R's and turning the subscripts into superscripts, into exponents. So r to the n equals r to the n minus 1 plus 6 r to the n minus 2. And then we want everything on the same side, and we also want to cancel as many r's as we can. So if we cancel, if we divide out n minus 2 r's, we're left with 2 r's here. So r squared equals r to the first plus 6. Now let's move everything to the left side. R squared minus r minus 6 equals 0. Now we need to know what are the solutions to this equation. So I picked an easy example to start with. We can factor this. R minus 3, r plus 2 equals 0. So we have two solutions, r equals 3 and r equals negative 2. So these are our characteristic roots. Let me label those. Okay, so then what our theorem told us was, over here now, I can write my general solution is an equals some linear combination of 3 to the n and negative 2 to the n. So it'll have the form, I'll call it alpha 1 times 3 to the n plus alpha 2 negative 2 to the n. All right. So alpha 1 and alpha 2 are any numbers now. So any numbers I could pick for these would give me a solution to this recurrence. So the general solution is exactly what I've written here. Anything of this form works. And I guess since I don't have, I want to keep these videos relatively short, and I don't want to go full hour and 15 minutes for all of them. I don't want to start a new example. Let's go ahead and take this problem and now add some initial conditions just to see what that looks like. So this is the part where I would ask if there's any questions before I erase. But all right, so let me keep the solution there, but erase the work. I'll move it up here. So if I have this same recurrence, but I also have some initial conditions, say A0 equals, I'm going to make up some numbers. I don't have this example prepared, so I don't know how bad this will end up being, but we'll say A0 equals 3 and A1 equals 4. Now it becomes like an initial value problem. So once I get to the general solution that I have here, I have something that will satisfy the recurrence. You can check if you want that if you plug this into this recurrence, you'll get a valid equation. All right, but now I need to know what alpha 1 and alpha 2 do I need to get the correct initial conditions. And now that's just a simple algebra problem. If you plug in n equals 0, I'm supposed to get 3. So if I plug in n equals 0, I'm supposed to get 3. I'll get alpha 1 times 3 to the 0 will be alpha 1 plus alpha 2. Negative 2 to the 0 will also be 1. So alpha 1 plus alpha 2 equals 3. Now if I plug in n equals 1, I'm supposed to get 4. If I plug in 1 over here, I'll get 3 to the first times alpha 1. So that's 3 alpha 1. Negative 2 to the first gives me minus 2 alpha 2. So I get these two equations with two unknowns, alpha 1 and alpha 2. Let me erase my in stuff. Now it's just a simple system of equations to solve. Let's see, if I multiply the first one by 2, could just solve this and then cut out my work. But if I multiply the first one by 2, I get 6 equals 2 alpha 1 plus 2 alpha 2. Now if I add, I'll get 10 equals 5 alpha 1, and my alpha 2's cancel. So alpha 1 equals 2. And that means back here, alpha 2 would have to equal 1. So it turned out pretty simple in this case. That was just luck, though. In general, you're going to get fractions of some kind. But that means my particular solution to this recurrence problem, this recurrence relation with these initial conditions, would be basically just plug in alpha 1 equals 2, alpha 2 equals 1. So this specific sequence is the solution to this problem. Right? Good. Everybody understood it. All right, so we'll do more of these. We'll talk about the other case for the theorem, and I'll do some more examples. See, it's 11:43. I feel like I have another hour in me. We'll see.